Hello everyone, welcome to this live webinar for coding about coding for invention. This is presented by KTBYTE Computer Science Academy, and it's also in affiliation with the Young Inventors program and the STEMI Coalition, which is part of the Henry Ford Museum of American Innovation. So today we'll be having three students from the KTBYTE Robotics program, which is a computer science academy right here in Lexington, Massachusetts, just 20 minutes outside of Boston. And we also have our facilitators, Nicole Bellabona, who's the director of the New England Young Inventors program. So basically, we have to first define before we can get into talking about our inventions, we first need to define what an invention is. So there are different inventions out there, and an invention simply is just a solution to a problem that we see in the world. This can include penicillin, which is an antibiotic, which has really helped and saved many lives and has increased our life expectancy in the later half of the last century. It also includes things like the modern car invented by Henry Ford, but it also includes more simple things like the pencil. As much as a simple idea it is, a piece of graphite stuck together with a piece of wood. It seems very simple and low tech, but it has a profound effect on our lives. Like, could you imagine what would happen if we didn't have a pencil? We wouldn't be able to do complex math, and as a result, we probably would have never gone to the moon. Now, there is a process to create these inventions, and the process is in 7 steps. The first is identifying the problem. The second is understanding the problem, researching the problem, understanding understanding like the different details of the problem, and then understanding how to solve this problem. Then ideating is writing down different types of solutions that you can use to solve the problem. Like, think, how could I use this? Could I use that? And once you have an idea to your solution, you can start designing. So you can design the initial prototype for your invention. And then once you have completed that phase, we can move on to the building phase, where we can actually start building our prototype. And then we can test our prototype, make sure it works. And once we're done with that, we communicate with others and gain feedback. So without further ado, I will talk about my invention. My invention is Seeing for the Blind. It is a project that I've been working on for the past 2 years. I started it in the fall of 2016. Now it's the fall of 2018. So let's start off by looking at this image. This is what legally blind people see. And we have to and this is when we first identify the problem. We know that legally blind people, or just blind people in general, have a degraded eyesight. And this means that they have a hard time finding their way and navigating. Now we've found our problem, we know that it's hard for blind to find their way. So we can research this problem and understand that there are 285 million people who are legally blind, meaning that their vision is below 20/200 vision, even with their glasses or contacts on. This is this image right here. And out of these people, 39 million are fully blind, meaning that they can't see anything whatsoever. And we can also understand that there are 2 different types of blindness. One is congenitally blind, and one is blind at birth. Blind at birth means that when you are born, you are blind. You have never seen anything in your life before. And congenitally means that something in your life, whether it be old age, cataracts, or an accident with your eyes, has caused you to lose your eyesight. So now we can start looking into like different ways that other animals maybe even try to find their way. The bat also has a lack of vision. But it uses ultrasound or echolocation in its terms to basically find the distance between itself and an object. So we could research about this problem and research about the solutions. And then we can also research what already is out there. So we can tell that there are some solutions out there, including the human guides, dog guides, canes, and even therapy. However, they lack distance, tiredly used, or only imported objects at ground level. They're expensive, inaccessible, unportable, and they don't tell you what specifically the objects are. So now that we understand the problem, we have to start creating ideas. We have to start ideating. And the first thing we have to think about is our project goals. What are we trying to accomplish in this project? So we know that we want to create a device that is made to find the distance between the user and objects in front of them, and the device must be able to communicate the distance to the user. So how are we going to do this? We can think about use technology to think about what the solution is, and these include using echolocation with sonars, or even using communicate using. We have to communicate this to the user by using sound. We can modulate both pitch and frequency. So now that we've done this, we can start designing our inventions. We can start thinking, what do we need to do? How are we going to basically build the invention? Where are we going to place it to get the best viewing angle? How are we going to draw it out together? Draw it out placed on the body. We can even start drawing out a basic schematic. And by the way, a schematic is a drawing showing all the electrical components put together. So your computer, your light, your battery, everything together. And we can start planning our project. And once we've done that, we can go into the building phase.
And this is a sonar. So you can see there's two small circles here. One is the trigger and one is the echo. So the trigger, it will send out a sound wave. And it'll go on a scale. It'll go beep, 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 and a wave outwards. And the wave will go and it will bounce off an object. So let's say I have my hand right here. Sound wave will emit out of the sonar, bounce off the object, and it'll come back and it will be taken in as an input in the echo. So it's a trigger and it's an echo. So what the sonar does is it doesn't actually measure the distance. It measures the time it takes for the sound wave to go from the sonar to an object and bounce back. So how is this helpful to us? How can we find the distance? Well, we know the time it takes for the sound to go and come back. And we know the speed of sound. So using that, it's a simple rate distance time problem where we can basically find the distance using the speed and the time. And we can find the distance between between the sonar and the obstacle in front. So that's the first bit of technology. The second bit of technology is an Arduino, shown right here. Now, an Arduino is a microcontroller. And what this means is it's basically, to think about it simply, it's basically like a small computer chip. Not necessarily in that terms. There's a few different distinctions between the two. Computer chip has an operating system. This one does not, but you can think of it as like the processing unit for our project. So very simply what it does is it takes in an input and it sends out an output. We can say put a thermometer, we can connect it to the Arduino, and the Arduino can read temperature. Using the temperature reading, we can output something. Say if it gets too hot, we can turn a light on. So it's a simple if this, then that. So in the case of my project, if the distance is this measurement, you output this sound. You'll output a certain sound frequency based on the distance that you see. Now, I can give you a demonstration of this right now. In this, you can see that in this graph, what we represented distance on the x-axis, and then frequency on the y-axis, and duration on the second y-axis, duration of the beam. And what happens is, as we are walking towards our object, in this case, it's the wall, as you walk towards the object, the frequency of the pitch, which means how close together the sound waves are. And if you think about it musically, it's how high up the note is on the scale, that will start to increase. And as you walk, as you walk towards the wall, the time in between each beat, that will get shorter and shorter and shorter, so that you're basically conveys to the user that you are approaching an obstacle in front of you. And I first built the first step of this. And it would be pretty deceptive to think that we're done. And I think a lot of you might think, this is great, it solves the problem, we're done. And I thought the same thing too. So I went to the 2017 Young Inventors program, or the Regional Invention Convention in New Hampshire. And this is me in 9th grade, and I was presenting my project. And a judge came up to me and said, this is great, but what if I'm walking on the street? Could I tell if there's a person in front of me? I said, yeah, because it's sending a sound signal out and you can find it up in a range up to 4 meters away. Okay, what about a stop sign? Yeah, you can see a stop sign in front of you. What about a box on the ground? Or what about a curb, a street side curb? You wouldn't know that's there because the viewing range of the sonar is 15 degrees, meaning it only goes 15 degrees outward. This is the viewing range of the sonar. That's all you get. So if I had a curb or a box or even a post box, like a mailbox down on the ground, I would not be able to see that, and the user would end up bumping into it. So there's a problem with the initial prototype. how do we see objects on the ground? Now, do we just give up and go home and call it a day? No, we tackle this like engineers. And by doing this, we open up another invention step. But if you go back to the very first slide, this process here, we enter into another invention process within the invention process. And then go back to identifying the problem. How to counter a ground level obstacle avoidance. How to counter a lack of ground level obstacle avoidance. How do we account for this? Now, what we're going to do is we're going to simply put the same system that we've implemented before on the ground so that we can see objects that are on the ground in front of us. Now, we've already understood the problem before. Based on using sonar. So now we have to we can start designing it. Actually, first we start ideating, but we've already, assuming we're using the technology from the first stage, we can just apply that to the ground. We have to start designing it. So now we are thinking about how to approach this problem. So we will put sonars on the shoes. That's clip-ons in the shoes. And why not just build it into the shoe? Well, we want everyone's shoe size is different. Your shoe size might be different than your mom's shoe size, which is different than your brother's shoe size, which is different than my shoe size. So if it's a clip-on, we can just clip it onto the tongue of your shoe. The tongue of your shoe is right right in front of where you tie your shoe, and then it can simply fit on anybody's shoe. So you can clip it onto someone's shoe, and they can work the same way using Arduino. And this time we have to think about how we're going to output the measurements. So can we use sound? Well, we're already using sound from before, so it's kind of confusing if the blind have to deal with two different versions of sound. What's another version? We have 4 senses left for the blind: smell, touch, hearing, and taste. Yeah. So can the blind is it easy to really create synthetic tastes? That's kind of difficult. It might be possible. Kind of difficult. Same thing that goes for smell. We're already using hearing, so the one thing that's left is touch. How can we use touch? Well, your smartphones vibrate all the time. Whenever you get a notification, every time someone's calling you, you're getting a new status update, you get these vibrations, and you can feel these vibrations. So now we can start building this project. So we're using sonar for distance measurement, using Arduino as a processing unit, and it's placed on the shoes for convenience. So this is a model that actually is a prototype that's built. And as you can see, it's built as like a clip-on or like a rig that's just Velcroed onto your shoes. So now we're building this, and it's going great, right? We're building this project, and we think this might be a game-changing product. But then we incorporate, we hit another roadblock, and it may seem like, why would I get involved in building an invention if all I'm going to do is fail again and again and again and keep hitting problems every 5 minutes? Now, the thing about this is that this is just the process of inventing. You will hit these problems again and again, but in the end, it will all work out. You can overcome every problem using more and more innovation, more and more technology, and in the end, you're able to create an invention that is really game-changing. That is how you make successful invention. Now, another issue we've encountered now is how to account for botched measurement values. So what does this mean? Well, we have a shoe here, right? And we have the distance measuring going outwards. And this seems to work fine when the shoe is placed perfectly on the ground. But when we're taking a step like this, our shoe is pointed downwards. And so the measurement value is pointed downwards. And we're hitting the ground right here. So that means that we're not measuring the mailbox that's like 2 feet away from us. We're measuring the ground. And that's not very good to have. We don't want to explain that measurement to the blind. You want to give another measurement. And as you can see, the same thing is illustrated here when your shoe is pointed upwards, where in this case, you're not measuring anything at all. So it may seem like, oh, there's nothing in front of me, where in reality, there might be a car inches away from you. So we need to find a way to account for these issues. And there are several solutions that are out there. One might say, why don't we put a gyroscope, maybe, a gimbal. A gimbal will basically keep it balanced and pointed in the exact same direction, no matter how you turn it. But that's pretty complex to use. And it's also very expensive. So how can we use something else? We have to go again and research some more. So another idea comes up is accelerometers. So what is accelerometers? Well, let's just break up the word. Accelerometer, acceleration. An accelerometer is basically a device a sensor that measures acceleration. So as I'm walking, whenever I pick up my foot, it will measure this, whoa, something's moving. And it measures this by having X, Y, Z values. So it will measure something X, Y, Z, and it will measure changes in X, Y, Z. So how can we do that? We can think, well, when there's a change in X or change in Y or a change in Z, we can assume that our foot is moving. And when our foot is moving, bad things happen. So that means that when the foot is not moving, good things happen. But when the foot is moving, bad things happen. So we can cancel out the measurements when the foot is moving and only relay measurements when the foot is not moving. So, and that means that means that your invention only works half of the time, only when you're standing still. But when you're walking, it doesn't work. Well, when you're walking, you walk 1 foot at a time. So left, right, left, right, left, right. So at all times, there will be 1 foot on the ground and 1 foot in the air. So now 1 foot's moving and 1 foot stationary. So using that, you're always able to have measurement. And say if you're even jumping in the air, you can revert back to the last known position. So after we've built this, we can then go to the 7th step, communicating. This was at Nationals at NICE in 2017. This is back in Washington, D.C., so it might look a little different. But right here is the shoe is right here, the glasses. So now we've communicated this, we think, all right, now we're done. We've done this, we've done everything, now we're finished. Nope. We're going back to the beginning once more, because then one judge says, all right, let me get this clear. You know where the objects are in front of you. Correct. Do you know what the objects are? Oh. I can tell if I'm walking on the street. I know that there's something in front of me. I don't know what it is, but it's definitely something. But how can I tell what it is? So now we have to go back to another problem. We identify the problem. How can we figure out what they are? If we're sort of researching technology out there, what are different ways? Well, the low-tech method is having a human guide walking around saying, that's a wall. That's a human. But a high-tech solution, because you want to let the blind be fully independent, is using a very complex system called machine learning. Now, I'm going to try to explain this in the simplest terms. How machine learning works is it's basically a computer algorithm that allows you to analyze an image or analyze anything for that matter, and then a computer will act as its own brain and predict an output. Now, if I take a picture, say, of an apple, I'll divide the picture up into its individual pixels, and I'll put the pixels into an input layer. I will put the pixels into an input layer, and now the pixels will be sent into these hidden layers. And in each arrow and each connection between each layer, some number will be multiplied by the input. And then you'll keep going again and again and again until you eventually get an output layer. Now, how do we create this algorithm and make it work like that? We have to train this. So what we do is, quite simply, we just take thousands and thousands and thousands of pictures of apples, and we put it into this network again and again and again and again and again. And we keep adjusting the values, these weights in between each layer. We adjust slightly again and again each time until eventually we finally get the network to say apple. And then we build off of that. We get it to say apple 50% of the time, 60%, 70%. We get it more accurate and accurate. Then we start adding oranges, then pears, then blueberries, raspberries, kiwis, mangoes, pineapples, anything. And we add again and again and again until we can grow this network. So this grows over time, and then eventually you can create a network that can take a picture of anything, analyze the image, and give an output. So for example, if I take a picture of the water bottle, what we can do is you can use a deep learning network to say the words water bottle. And we can also even apply this to text recognition, where we can take a picture of the exit sign and we'll read back exit. So using this, The blind are able to get both eye-level obstacle analysis and ground-level obstacle analysis, and then together they can get, and with this, you're also together with just these two components, you're able to understand how far an object is, and then using machine learning, they're able to understand where an object is or what an object is in relation to them. And then together with all three of these combined, the blind can get full spatial awareness. Now we have to start thinking about the cost. How expensive is this going to be? Now, if we sum up the total price altogether, we can tell that this is going to be around $60. Seems a little bit expensive, but this is for the cost of the prototype. And there are many different components in a prototype. And among them, there are two very expensive ones. One is $13, $18. They're both the Arduino microcontrollers. Now, one important thing to keep in mind whenever we're building a technology project is that the prototype is always more expensive than the production version. When we mass produce something, it can get much, much cheaper. There's many different factors involved. One of it is just simply that you're just producing so much at a large scale that you can drive the price down. Another is that you are also by using these different microcontrollers, when you're mass producing them, you're making a custom built version. So this project only uses maybe around 40 to 50% of the capacity of this microcontroller. When you mass produce it, you can make a smaller, simpler version of it, and you can just drive the price down. So the price should be projected to be around $5 to $10. So now the last thing is communicating once more. And this is in September 2018 where I communicated the invention again. And now I'm getting even more feedback to continue to grow my invention over time. So that is basically one example of how you create an invention. This is my example of it. Now we have another student here. His name is Boyan Litchev. He's one of the students at the KTBYTE Advanced Robotics program in Lexington, Massachusetts, and I will let him come up now and introduce himself.
Hi, my name is Boyan Litchev, and my project is a firefighting robot. So the problem that I tried to solve is that fires, on average, 7 people die in home fires every day in the US alone. And in 2015, over $14 billion were lost because of property damages due to fires. Then, in order to get a better idea of fire statistics, I found two graphs on FEMA about the fire dollar loss from 2006 to 2015 and the fire deaths from 2006 to 2015. I also did some research on some existing solutions, such as Thor, which is a military robot that is designed to extinguish fires on naval ships. Also, I found that drones and planes are being used to help gather information, and planes are being used to spray out fires. However, drones are not being used to spray out fires as of now. I also found out about some existing firefighting rovers, such as the Thermite T2. However, the Thermite T2 is very expensive. Because of all this, I decided that I needed to make a better solution. And for that solution, my project goals were to help detect and extinguish fires in an autonomous and inexpensive way, to be able to extinguish fires anywhere for a low cost, unlike the Thermite T2. My robot needed to be able to accurately detect the fire, to be mobile, to be inexpensive and generally accessible as a consumer product. It also needs to be able to spray water to extinguish the fire, and it needs to be able to withstand fires at a distance. In order to incorporate all of these solutions, I decided that in order to be mobile, I would use stepper motors for the most control over my robot. In order for it to be able to accurately detect the fire, I would use IR, or infrared sensors, which work by measuring the amount of infrared light or heat that reaches the sensor. And in order to be able to spray water, I would use a pump. I would use a pump to pump out water through a hose onto the fire. In order to be inexpensive and generally accessible, I decided that my robot should be made of plastic. And finally, in order to be able to withstand fire at a distance, the motors could be used to take the robot to a safe distance from the fire. For all of this, I made a code map about how my robot would need to work. It would need to work by first scanning for a fire. Then, if the robot detected a fire, it would need to start turning until the fire was detected on its front IR sensor, which is right over here. Then, the robot would know to stop turning because, as you can see here, the front IR sensor is aligned with the pump, so that if a robot detects a fire on that sensor, it knows that it is at the correct angle to extinguish the fire. Then, after it was at the correct angle to extinguish the fire, the robot would be able to turn on the pump and flash the LEDs to signal that there is a fire and to extinguish the fire. In order to create all of this, there are two coding platforms that I used, Openscad and Arduino. Openscad is computer-aided design software that allowed me to 3D print all of the parts I needed to create my robot, such as the motor mount shown here. Arduino is the programming language for the Arduino microcontroller, as Sid showed, and it allowed me to control and integrate the robot's sensors, motors, and pump to create an intelligent robot. Then, in order to get feedback from judges, I went to KTBYTE judging sessions and the regional and national invention conventions. There, the judges told me, okay, good, you can see at what angle the fire is, but can you measure exactly how far away it is? And in order to solve this problem, I decided to use another IR infrared sensor. This would work because the robot always sprays out water in the same position relative to the robot. Because of this, an infrared sensor can be angled so that the path of sensor detection ends exactly where the water is sprayed out. Because of that, if the robot detected a fire on that sensor, it would know that that is in the correct position to extinguish the fire, because the fire would need to be on the ground and it would be at the exact point where the water is sprayed out. I also made a new code map about how the robot would work once this change was implemented. Instead of the robot immediately turning on the pump and flashing the LEDs after it stopped turning, it would, after stopping to turn, move to a position to extinguish the fire, and then turn on the pump and start flashing the LEDs. Thank you.
All right, thank you, Boyan. So Boyan is a sixth grader at Diamond Middle School. So we have another presentation by Jonathan and Harry, who created their own invention called RoboPostal. And unfortunately, they were not able to make it today, but I am subbing in for them, and I'm just going to talk briefly about the project and how they built it. Now, this project the problem that they have is that short distance deliveries between two different places is very inefficient and expensive. So they're trying to solve this problem because right now short distance deliveries are carried out by things like UPS trucks, and they're trying to solve the problem where they create an invention that will be able to deliver this autonomously without having to use mailmans in trucks to deliver them. They want to create a small robot. Now, they also did a little bit of understanding out there to see what else is out there. They looked at these Amazon Prime drones that try to do short distance deliveries by air, and even USPS trying to do something as well. But they ended up building an invention. They ended up building an invention using Arduino once again to create a robot that can navigate the streets and can deliver packages from point A to point B around the city. And then they started thinking about what type of technology use. So Arduino they've chosen already, and and as you can see here, this is the board they use is an Arduino Mega, which is a different variation of an Arduino. There are many different Arduinos out there, some including Arduinos, which is the one that we talked about earlier, and some are even MKR1000, which is what I used in my project, which is a very small version and this is a very large version, a very high-powered Arduino. So they first started to use Arduino, and they're also using GPS to find their way. I'm sure a lot of you know what GPS is. If you ever have to drive to soccer practice or a friend's birthday party, you use GPS to get there because you may not know where the location is. I'm sure, especially so every time for me, I always use GPS to go to the regional invention convention. I have no idea where that always is. So what we So they use GPS to basically, and GPS stands for Global Positioning System, and it uses satellites to basically locate your position on the globe and figure out where you are. And that's why when you can open a map and it's using GPS to basically put a blue dot where you are on what street you are, and then a red dot on where you're trying to go, and they'll map out a position for you. Now they've also been using something called ultrasound sensors, which is the same technology I used to help prevent collisions between any objects. For example, if it's driving around and hits a wall, we don't want to hit a wall because then the entire thing crashes. And so instead, by putting these sonars on, the robot is allowed to basically avoid the obstacles, turn around, and keep moving. Now they go through some feedback. Of course, so basically, this is the building step. They build a prototype, and it says the initial. So, and what what they did was they created multiple versions of the prototype. They first built an initial prototype, which is extremely basic, and what they did was they had buttons on the robot, and it was and it's not like go left by 3 feet, turn right by 8 feet. No, it's literally left, right, and go backwards. These 4 buttons: left, right, forward, backward. And what it would do is they would say left, left, forward, forward, and then go turn left, and then go forward. So it was a very simple prototype, and it worked.
Let's start up our robot again. It turns right, goes forward, turns left, and then goes forward to our final destination as expected. We can scale this up to any size we want, and the robot will still be able to get to its final destination in the most efficient way possible autonomously, assuming it's not going diagonally.
So, as Jonathan expected, he's tested this many times before, the robot functions in that way. So then they're going to start using a more complex version where they mapped it out in a grid. So in math class, a lot of you might have been drawing graphs of lines, or you might be familiar with grid paper. A lot of math teachers love to use grid paper, but it's basically you have different lines in a grid. And it's these small squares, and all these squares are organized around. So they base this off of the city block. If you've ever been to New York City, Boston, any major city, you notice that all the streets are in a grid. They're all parallel streets. There's one set of parallel streets, one set of other parallel streets, and they're perpendicular to each other. So they always cross each other at different points. And what they did is they based their technology off of this. The next prototype is using a grid, and they would navigate through the grid, moving along the lines, kind of like a maze. One of those mazes you get maybe at the kid puzzles. There's a little maze. They move down, right, down, right, down, right. And they basically put it as a coordinate grid. They say, I want to move from point 0, 0 to point 1, 1. And I'll go right and then up. So that was the next prototype. Then they started to use GPS GPS to make this even more advanced so that it can function by itself. So here's a demonstration of this.
So let us plug it into right here. Then we'll need to calibrate this, which is the magnetometer. The magnetometer or compass has calibrated, and right now our motors are spinning. Right now what it's trying to do is to align itself with the correct heading. So let's say that I put this on the ground, then it turns over here. If I put it over here, it also turns to that same exact spot. Now, let's kind of see this in real action. So, if I put this down right over here, the robot always, no matter how far off it is from its course, keeps itself back on.
So then there's feedback. And he presented at the National Invention Convention, and he got feedback from many judges around there. So this is Jonathan, that's Nicole, who's right behind us. And then they told him about different solutions. They told him a lot of feedback. He was able to build off that feedback, create these different solutions. So he started designing again and then building the solution. He decided to add GPS and a compass to help the robot align itself. And he also developed an AI algorithm that can help him find the best route to the destination. Because there's many ways to take a very long route, but there's one way to take, or maybe one or two ways to take the shortest route. And we want to save time, so we will always take the shortest route. So he created an algorithm to always find the shortest route. It went through and got some feedback. He was also presented on the show Innovation Nation at the NICE 2018 in the Henry Ford Museum in Dearborn, Michigan. So he faced many challenges along the way. And as with any project, we had many challenges. Our final code was over 12 pages long. That's printed out pages because we love paper. It had an AI algorithm and could use GPS and compass. It had an LCD screen to display the coordinates you're going to. Our biggest challenge by far was the GPS and compass system, but we were anyways open on trying new things, and we never gave up. That is, I think, the mantra of every inventor. If you ask any inventor who's created a life or a game-changing or world-changing or life-changing product, and you ask them, did you get it right on the first try? I can almost assure you that almost nobody got it right on the first try. Maybe this is one person who got lucky, but the chances of that is like 1 in a million. You always encounter some problem along the way, but it's what makes an engineer, it makes an inventor to find a way to go around this problem, find a way to do this. And a lot of you may be concerned about how to solve certain problems. And that's why we're trying to help you introduce technology to use that and solve the problems that you see. So we have Alexander's son. He is one of the other instructors at KTBYTE. He's also the instructor of the advanced class, which trains students for the National Invention Convention. He will be here to talk about some different technologies. Here is Alex.
So I'm going to be talking a little bit about how you can maybe get started. Maybe you don't know anything about this Arduino stuff. What are they talking about? I'm gonna give you a few tips on how you can get started on integrating technology into your project. So first, I have one general rule. Is that technology is great. Can it solve everything? No. Does it need to be used to solve everything? Absolutely not. So I've worked a lot with both electronics and very high level stuff, as well as very low level stuff. And the first thing that I would say is, if you have an idea, you might not need technology at all. There are very many different solutions, and there are many different ways to do it. Technology is sometimes a very efficient way of doing it in a very fast way, but does it need to be used? Maybe not. All right, so let's say that now that you have decided, okay, I've thought about this, and I don't really think that I can do it without technology. So where do I start? So we have a list of these slides, and they have all of these things, okay? So where I would start is always do your research. So say you have a very specific problem. Some of these things will work better than others, and some of these things might be completely overkill, all right? So first, I recommend an Arduino. So it's the simplest of all of the types. So what you see here is we get a board, something like this, something simple. It's what, 15, 30 bucks? Not very expensive, right? So what we're able to do with it is we can easily connect it up to our computer, right? Download a free piece of software, and we can start writing code, telling you how to do things. So things on this level are called microcontrollers, or for our case, we'll just basically say it's a mini computer. So when we have a mini computer, something that we're allowed to do, we should know what this board can actually do. So what you'll see here is that we have mainly one specific thing that this thing is used for. We have one type of pin called the digital pin. What does it do? Turns things on and off. That seems very, very vague, very low level, right? It's like, what can I really accomplish by just turning something on and off? So what I mean by turning something on and off is just giving electricity or turning it off. So on the most basic premises is that means that what we can do is we can let the board control things. We can give things out. We can tell something else to do something, or we can take in something and figure out what it means. So once we have started with one of these, say you bought a board, then we move on to very, very basic like circuitry type thing. So that may sound something like really advanced, like something that comes out of like a physics textbook, but it's not the most complicated thing. So it's basically just make sure that you connect everything well. There are diagrams all over. I won't be explaining that right now. So moving on, we the most basic thing to use for prototyping an electrical circuit is a breadboard, one of these. So what this allows us to do is, so in something like a manufactured electronics, what we'd see is you open it up and you'd see a jumbled mess of wires, plugged in, connected, soldered on to other things. And you think, how can I do that? I don't even have an idea of what circuit to make yet. How do I do this? So what we do is you can take one of these boards, right? And you just take a bunch of wires and maybe something like a light bulb, let's say a light bulb. So what this allows us to do is we can literally just take wires and just plug them in. And when we don't want it anymore, say we did something wrong or we want to make a different circuit, just unplug it, right? Simple as that. So what that allows us to do, that allows us a whole nother realm of to allow us to experiment. So now what we can do is we can mess around, we can play with things, we can get them to work without risking destroying anything or putting in hours and hours of time trying to figure out how to get these two things to connect together. And when they do connect, the thing doesn't work. So those would be my first steps, is to get a basic knowledge of how circuitry works and just buying an Arduino. So moving on, the next step that we would want to take is we would want to implement a single sensor, a single thing that we can give an output or take in an input. So that is the first level to making something to solve a problem. So our board on our own is really cool and all, but all it can really do is just take things in, give things out. But where are we taking the things in from? Where are we giving them out from? So let's take the sonar that we've heard so many great things about, right? So here's another image of it. So we have this thing, right? So how do we make our board understand what this does? How do we make our board able to control this? So what we're able to do with something as simple as a $30 board in this is that we can make it do distance, right? So what we're able to do is it's just as simple as telling the board to tell the sensor to send out a signal. And then when the receiver gets the signal back, all the sensor is doing is sending the board a signal saying that, okay, I got the signal back. And then the board will be like, okay, I received that signal. And then you can determine what to do next with it. So now that we've like hooked up these sensors, so that's one generalized sensor. Here's a very long list. So there are very many different sensors that you could use. Just to give you ideas for now, is that you can have gas sensors. So that means that you can have, if you wanted to make like an in-home gas checker, you could have it check for carbon dioxide or carbon monoxide. There are flame detector modules. There are temperature sensors, water sensors, humidity sensors, even things so much as fingerprint sensors. All of these can be implemented in your project. Now, okay, so now you've done your research. So you have your board, you have your breadboard, you've bought the sensor, but you have no idea how to do it, right? So we've explained the very basics premise of a sensor is that you tell it to do something and it'll send you some piece of information back. So the next part is that we have to do more research, right? So we've seen all these great ideas and it's all about the research. It's all about figuring out how to do it. So let's take one of these, say, fingerprint sensors. So you have this, so a fingerprint sensor is really complicated, as you know, it's a biometric scanner. So, well, the sensor does it for us. So what do we need to know about the sensor? So we need to know how to tell it to do something. And we need to know what type of information it's going to send back. And then we can just have our board interpret that. So basically what we do is we go on to the internet, we look it up, right? There's documentations for everything. There are data sheets everywhere. The internet is the greatest resource that we have ever had, right? It's better than going into a library and looking for a textbook on sensor and then realizing that no one would write a book about a sensor. So yeah, so after that, what we could do is we'd figure out all of the specifics on how to do it, and we'd figure out how to get the singular sensor working. So now what do we have? So now we have a sonar sensor that works on its own, and now we have a fingerprint sensor that say works on its own. So now how do we combine them? So we have our board, right? So our board it can give out inputs, it can take inputs and give out outputs, but it also has the ability to process them. So it comes with a processor on it. And what that allows us to do is that allows us to do operations. And in the code, we can specify what we want this Arduino to do. So the board comes with a programming language. It's called Arduino. It's really quick to learn. It's really basic. You can definitely get the hang of it after 1 or 2 tutorials. I assure you that. So now that you have a board and 2 different types of sensors, you can use the processor. You can program it to do what you want. So say maybe you have some type of lock mechanism. So what we want to do is we want our sonar to see if there's a person in front of us. So what happened is that when the sonar sees something, it would send it to our board. And our board will process that image like, okay, there's a person there. And now what maybe the board would do is it would turn on the fingerprint sensor, say you wanted to conserve energy or wanted to just know if someone is there, or if it was, yeah. So now that we know that there's someone there in front of us, it will turn on, we can use the board to now do a separate output and turn on the digital fingerprint sensor. And then what we'll do is we'll have it wait for a signal from that. And whether or not that was true or not, we could use the board again to control a separate lock that would either unlock or keep the door locked. Right? So that's like the very basics of how to start and get a very simple project and multiple sensors working together to create a more complete project and a more nice solution, a cleaner solution to say a problem that you wanted to solve. Yeah, so along the way, we have various other things that we should probably do along the way. So we have this idea of proof of concept. So I talked a lot about prototyping on this breadboard, right? So on this breadboard, what we probably end up doing is that we'd probably end up with a jumbled mess of wires that like you could probably accidentally unplug, right? But what it does serve is, as a prototype, it might not be the most useful thing in the actual world. We might not be able to actually use, like, it's a proof, we might not be able to actually see a true implementation. Say that lock system I was talking about. If we had this board and all the wires plugged in, you'd have to think about actually mounting it to the door. But that's not the point here. The point here is creating a proof of concept or a prototype. And once that is determined, we can start thinking of much more cleaner ways to actually implement it into solving the actual problem. So proof of concept, what it does is allows us to test and make sure that our thinking actually works. So both of the projects that we've seen up here are very good examples of proof of concepts. They both are definitely prototypes, and they can definitely be optimized for the actual market. And I would love to see their steps into the future. So how do we take this up to the next step? So actually, no, we're not going to talk about that. So kind of continuing with the prototyping, I don't think that many of you guys are looking at that stage yet. So we're going to continue with proof of concept. So we're going to move into more complicated things, more detailed things. So cool, we do have this breadboard circuit. Now, how do we get it to actually fit the scenario that we want? So going back into something like the lock problem that we've been talking about is that, well, so now we need to think about more mechanical ideas. We figured out the circuit, we figured out the actual like hard part, or per se hard part. Now we need to figure out how to mount it on the wall, get it to interact properly, get it to work in the right places. So what we can now move on to is I would recommend woodworking, very basic, by hand saw at Home Depot. Right? Yeah, I was gonna. So first step, you have nothing else, woodworking. Wood is great. Wood is cheap. You can hand saw it at home. Nothing fancy, nothing large, nothing that'll break your bank, right? So woodworking, perfectly fine for prototyping. You can get another even better one. And then after woodworking, say we've done that, you could invest in something like getting a 3D printed, getting the parts 3D printed, and learning something like computer-aided design or CAD. So Boyan touched on this, but what he was able to do is he was able to go online, use free software, and design this part that would be specially made and specially mounted for his specific components. And now this is not something that takes very long to learn. It's very much a practice thing, right, to get good at. So once you've done that, say you've borrowed a 3D printer from like a local shop, now you have this perfectly created piece for exactly what you want, and we move another step closer to getting a complete idea or a complete kind of design. And what this does is this makes your proof of concept more functional in the real world. And what that's able to do is that's able to better prove your concept more because it's usable now. People can, while they might have seen a jumbled mess of wires before that sure does what you want it to in a manner of speaking, like it takes my fingerprint, it sees if I'm there. Now what we're able to have is we're able to have something that might actually work, a singular prototype that will work the exact way you want it to, the exact way on the actual thing that you would want it to. Now, say we've gotten to that stage. So now that we're at the stage of basically having an almost complete prototype. So what can we do now? We can, if we really think that this is the best idea, we can go to figure out a way to get it manufactured. But we can also go back and look at things. So as Sid and Boyan touched on, there's a lot that they could have added, and there's a lot that they did add to their first prototypes of the project. Now, they talk a lot about failing and how miserably long it took them to get to the correct place. And I assure you, it will take quite a long time, but not too long. It's definitely doable. And the product that you see at the end is very much something that you should be proud of. And as you keep working, it's the idea of going back, revisiting things, refixing things. Maybe say something was slightly out of alignment, just going back and fixing that one thing, just recreating it, reworking on it. And what that's not just able to do is that's able to, one, further your idea, but two, it's allowed to teach you something valuable. And I mean, at our level, at our age, at the high school, middle school, elementary school level, it is about learning, right? So what you're able to learn from this is, so at the beginning of the project, you're a kid watching a computer screen. Say you knew how to do some really basic things, and now what have you learned? Just look back at your journey. You've learned electronics, you've learned breadboarding, you've learned prototyping, you've learned 3D printing, you've learned woodworking. You've learned all of these tools that you can go and use to solve new problems, more problems, problems of the future that will come up. And I will assure you that you'll be very proud of yourself, and you will absolutely have all of these knowledge and all of these resources to go on into the future and go solve tomorrow's problem.
All right, thank you, Alex. So as Alex mentioned, there are many different solutions that are out there to build your invention. And we hope that this has given you a good understanding on different technologies that you can use and the things you can use to further build your invention and make it more, either solve problems that otherwise couldn't be solved, or think of new ways to make a more efficient solution. So now we're going to hear from Nicole, who's going to talk about the Young Inventors program in New Hampshire.
Thank you, Sid. As I mentioned earlier when we started the presentation, I'm Nicole Bellavana, Director of the Young Inventors program of Northern New England. And we actually have schools all across New Hampshire and now Massachusetts that do our program within the schools, either as part of the curriculum or as an after-school program or an extended learning opportunity or club in Sid's case. So we encourage you to, if you don't have the program, if you're not familiar with the Invention program, definitely seek it out. It is of no cost for schools to do, or YMCAs or organizations can sign up to do the program. And you can send your Invention Convention winners. So you would have a science fair style Invention Convention, if you will, as they do at KTBYTE, and send your winners to our regional competition. And we will send you, if you're a part of the program, we will send you medals for your Invention Convention so that you can get your first, second, and third place winners, something nice to represent all their hard work in inventing. So we encourage you, if you're not familiar with the program, to think about inventing and ideating something new and original, like Boyan and Sid have done such a fantastic job of. And the KTBYTE folks that have worked with the students in the Invention program have really helped kind of bring those inventions to the next level and really do some amazing technology integration. So if you have any questions about our program, definitely feel free to reach out. Again, it's the Young Inventors Program of Northern New England with the Academy of Applied Science, and we're happy to get your school or organization started so that your winners can be on a path to inventing as quickly as possible.
So earlier we had the folks from the KTBYTE Robotics Club. Thank you, Sid, Alex, and Boyan for sharing all your knowledge. So just briefly, KTBYTE teaches computer science to students ages 8 to 18. Our curriculum is progressive. We have beginner, intermediate to advanced classes. And essentially our strength is in our advanced classes in that we teach college level computer science to pre-college students. So yeah, definitely check out ktbyte.com for more information. And I actually would just like to open the floor for questions for Sid and Alex or Boyan, if anyone here has any questions.
Yeah, so anybody maybe online have any questions, you can just type it in the chat box on the side. Anyone here have any questions? I just want to mention very briefly that if you are in around the Massachusetts area, the New England, New Hampshire, Massachusetts, maybe even Northern Connecticut or anywhere, and you need help maybe trying to integrate technology into your invention, just in the invention process in general, KTBYTE is located not too far away. We have students who commute from all across Massachusetts, even New Hampshire, for classes on how to advance their projects. So at the Robotics Club, we have 3 levels. We teach you the very basics of Arduino. We move up, teach you more advanced Arduino, and then in the end, we help you build your own inventions and your own projects so that we help you build an invention, make your prototype, keep a good notebook, make a good pitch, give a good presentation, and we help you go to competitions. And our intent is making sure that you create inventions that will win and will benefit the world. So with that, is there any questions we have either online or? Yeah, so the question that someone in the audience asked is, where can we buy the parts? Home Depot might sell a very limited amount, but any hardware or computer store sells these parts, including places like Micro Center. I see there's a store called You Do It as well. Yeah, many DIY shops. Yeah, so there's also maker spaces out there. There's a maker space in Cambridge called Artisan Asylum. I think you need to be 18 to use it, however. There are many maker spaces across the country, depending on where you are. But just look up maker spaces near me, or even robotics stores near me. For vast resource to buy things is the internet. And maybe many of you might have Amazon accounts. So you can buy maybe even a water sensor, and you can buy it off of Amazon, and they'll ship it to you using Jonathan's RoboPostale robot. Maybe in the future, but we can ship. You can buy things off of Amazon. Another place is Mouser Electronics as well. You can also use maybe Alibaba, or perhaps there's a website called SparkFun and Adafruit. I would shy away from SparkFun and Adafruit. They don't really give too much documentation on the sensors, but there are many resources out there. So the feedback from judges is, I would say, is probably one of the most useful parts of the invention process. Because you think about it this way, when you're building your invention, you only know your invention from the perspective of yourself. Using your perspective, your personality, you are able to judge your invention, and you can think, okay, this is a good idea. But because it's just you may not know what the solution, you don't know what kind of problems may arise or how you can even make it better. So if you get external feedback, you are able to really grow what you need to do, what you need to do to improve your project and make it better. So especially getting feedback from the National Invention Convention, they have amazing judges there who give expert feedback. We have thought that the feedback from the Invention Convention is so profound that we've decided to even do it at KTBYTE. So every few months we have our judging sessions where we give experienced students to present their projects. So they get experience presenting the projects. So I'm speaking in front of an audience of maybe around 50 people. We also have a panel of judges. So they can comment on their projects and give them useful feedback. And to be honest, there's a lot of feedback that we've heard from judges that we haven't heard, we never even thought about. One student created an air vent cleaner, and then someone said, what if the machine breaks down? How do how do you bring it back? It's stuck inside an air vent. And those are different solutions that you might not think about, but having judges is a very important key to really building your project. You get external feedback and you are able to understand what to do next to build your project. This question is, what is the most challenging problem that Boyan faced when he was building his firefighting robot?
I would say that the biggest problem I faced when building my robot was probably controlling the motors, because voltage spikes could destroy the stepper motors. And because of that, I needed a motor shield that wasn't very easy to use. Also, learning Arduino in general did take time for me.
Why don't you explain what a stepper motor is?
So a stepper motor is basically a motor with steps. Here's an example of a stepper motor. And I used a stepper motor instead of a normal motor because stepper motors are more controllable.
So one thing to note is that Boyan has started learning Arduino. When did you start? You started last July, right?
Yes, I started last July.
Yeah, so he was one of our initial students who started. And within 1 year, not even 1 year, but from July to March, he has been able to learn Arduino. So it's definitely not something too hard to pick up. And through the KTBYTE classes, he's advanced from beginner, intermediate to advanced. And he was able to build a project, even build his first prototype within a week, all by himself. So that's something pretty important, or pretty profound to say. And just to let you know that Arduino is not this far off concept that's hard to use. Arduino is basically it is something that is used all around and it's many different things. For example, the flashlight, when you turn it on, there could even be an Arduino controlling, like maybe when you're blinking a light or you're just keeping it on with the different brightnesses. There's an Arduino control. It can be like a small microcontroller like an Arduino controlling that. And basically, our microcontrollers and Arduinos are found in many different parts of technology, in many household products. So the fact that it's being very widespread is well documented. So you can use the internet as a resource to really understand how to build your project. So it's definitely not too hard to use. But yeah, anything else? So the question is, what are some online resources that students can use to self-learn? You can use the Arduino website itself has a lot of resources. Additionally, there's a website called maybe SparkFun and Adafruit. You can buy sensors from there as well. It's not too great of quality, but they give a little bit of explanation on your sensors. Another thing is even maybe getting books themselves. This is the book by Maker Faire. It's called Make Electronics. Might be hard to see, but just anything using Arduino, just an Arduino book in general. Even the SparkFun SIK guide. It's kind of hard to find, but it's a very useful book as well. Alex has some other points to make about that as well.
I actually learned Arduino completely off the internet. So I didn't really have a teacher like we have these kind of programs now, but back when I was learning it, I did not. So kind of the way that I learned it, I think that the best way to learn it is to go out, buy a kit. Comes with like some more sensors that you can ever need, a nice board, cables to connect to your computer. And yeah, that's the first step that I would say. Just go out, buy one, commit to it, okay? So then once you've bought the board, now you obviously want to know how to use it. So first of all, very many of these people that sell them, they often throw in like a tutorial. It won't be the best, but it does the very basic. So going on along with this, to add on, YouTube videos, YouTube tutorials are great resources. You want specific websites, the Arduino website itself has a great getting to start guide from like zero knowledge to getting you to pretty far along. As Sid said, Adafruit, SparkFun, while they may not sell the most high quality of parts, they do very well. They do very good explanations. They do very good explanations of motors, of all types of components. And if you're more interested on the circuitry side of it, they do very good circuit tutorials. And kind of adding on to that, if you really want to get into like the circuitry side of it, making more complex circuits, I would recommend this website called All About Circuits, where you can literally go in and like there are like multiple categories. You can learn about DC, AC. You can learn about controllable circuits. there's vast amounts of knowledge out there. Even just a simple Google search, Arduino getting started, or Arduino specific component, Arduino, how do I do this? Like, there are forums, there are threads, there are people that you can ask online that will give you answers back. There are always people that are going to be more experienced than you. And the online world is a great way to get into contact with them. And they love to help people. They would love to help you.
All right, thank you. So I hope that this has provided some information on how to further grow your projects, and I hope that you can get out there and start inventing now on your own. So once again, thank you for tuning in. If you're watching this later on, thank you for watching this, and thank you for the audience who has come here as well. And thank you once again to Nicole and KTBYTE for letting us do this webinar. And yeah, good luck inventing. Good luck doing your projects, and I hope we'll see you at the National Invention Convention this June.
my name is Harry.
And my name is Jonathan.
We came up with RoboPostal. So in the current situation, delivering items short distances is very inefficient and expensive. So, for example, if you wanted to deliver a small package to a neighbor, this could cost up to $10 and take up to a full day to process. So we thought to ourselves, how can we fix this issue? So first, we looked at companies that are already trying to solve this problem. For example, Amazon Prime Air is already trying to develop drones that will deliver things to people's houses. However, this would not work well in cities where the drones would have to fly through the buildings and it would be impossible to fly in apartments. So we would have to design something that would implement all the positive features of companies such as Amazon Prime Air and negate or improve all the negative aspects of them.
So we thought to ourselves, why not simply create a robot that can navigate along the streets? Well, that's exactly what we did. Here we have created a robot where the top is for like the payload, where we can hold like items like the cargo. Here we have the actual battery. This is what powers this, which is an Arduino. An Arduino is a microcontroller, meaning that it can control how much power and energy goes to these two things, which are called motor relays. These can amplify the voltage to these, which are the actual motors. However, not all our work was with the hardware. We actually also worked a lot with the software. Our software actually allows us to tell the robot to get to some place and tell the robot where it starts off, and it autonomously gets to its final destination in the fastest way and most efficient way possible. So, let's explain a bit more. When we power up our robot, it creates an imaginary grid, with each grid spot containing how many steps it would take for us to get to that grid spot. From our final destination, we can trace our way back using the grid spots with the least number of times of steps it took for us to get to those grid spots. Adding those to a list, our robot now knows the most efficient routing. So, if we look at our robot, I've set the destination spot to be about right here. Now, our robot cannot do any diagonals, so we would either have to go to this grid or this grid. Both of them are the most efficient, but let's just see how our robot reacts. So, let's start up